I welcome you all in this presentation related with the subject fundamentals of surface engineering, and we are talking about the surface modification techniques. And under the surface modification techniques, using the surface composition modification for improving the surface properties, we have talked about the two approaches. One was the carburizing, where carbon content is increased at the surface and near surface layers, so that after the required post carburizing heat treatment, suitable combination of the properties can be realized. And the second process was the cyaniding, where both carbon and nitrogen addition is used for improving the surface properties. But in the cyaniding, the role of the nitrogen is much bigger in improvement of the surface properties than the carbon. In both the cases, we need the post heat treatment, post carburizing or post cyaniding heat treatments, so that the required phases and compounds can be formed, so that the expected improvement in surface properties can be achieved. Now we will be talking about the third process under this category, where primarily diffusion is used for surface composition modification. So, carburizing also uses the diffusion, cyaniding also uses the diffusion, and nitriding also uses the diffusion for modifying the chemical composition of the surface and near surface layers, so that the required improvement in surface properties can be achieved. So, as the name appears, in nitriding, basically the objective is to form the nitrides at the surface and near surface layers. And all types of the nitrides may not be good, especially nitrides of iron, chromium, aluminium, vanadium, molybdenum, titanium. Those nitrides which are stable, which are hard, and of course they are accompanied with the increase of specific volume. This is not the target, but increase in the hardness is the prime objective. But when it occurs with the increase of specific volume, we get the benefit of both increased surface hardness and developed the residual compressive stresses, and both these properties help in improving the tensile strength, fatigue strength, as well as wear resistance of the material. And that is why nitriding helps to improve the wear resistance, at the same time the mechanical performance of the component. So, what is the basic procedure for this? So, for the nitriding purpose, the steel component which is subjected to the nitriding process, basically the nitrogen content of the surface and near surface layers is enhanced. It can vary like say up to 5 to 6%, and when the nitriding is carried out. The objective is to form the nitrides which are hard and stable. At the same time, they do not enhance the brittleness and increase the cracking tendency. So, when the nitriding is performed, we will see that the nitrogen concentration, like carburizing, is higher. Nitrogen concentration is higher at the surface, then somewhat lower at the subsurface layer, and then further lower at the in the further deeper zones away from the surface. So, at the surface we may have like 5 to 6%, then 3 to 4% in the subsurface layers, then 2 to 3%, maybe less than 1% as well in the subsurface zone. So, accordingly the different types of the nitrides are formed at the surface, and these nitrides which are formed at the surface, which are extremely hard, very brittle, and they are crack sensitive. Although hardness and brittleness reduces the friction coefficient, but increased sensitivity for cracking increases the chances for the fracture through the growth of crack. So, once the cracks are developed, then these will be acting as a stress concentration or stress triggers, and thereby degrading the mechanical performance of the component. So, if we try to plot the variation in the nitrogen concentration with the increase of the depth and the kind of compounds which are formed at the surface. So, just systematic understanding, if we make a very top surface layer, this has oxides and very high nitrogen nitrides. This is of 1 to 2 micrometer thickness, and this because of high hardness, it helps to reduce the friction coefficient, that is the mu, or the friction coefficient is reduced, and it also helps to control, it also helps in like controlling the corrosion, means corrosion resistance is improved because of the presence of this. Then another layer which is like formation of the Fe4N, the gamma nitride. This can be of the size range like 5 to 20 micrometer. This very effectively reduces the friction coefficient, it increases the hardness, and it increases the wear resistance, but only problem is that it also increases the cracking tendency. And both these two layers are called the compound zone formation or diffusion compound layer, where the compounds are being formed, and in the further lower zones we will have the further lower concentration of the nitrogen, and this will be the diffusion layer. Diffusion layer, and the width of this or depth of this diffusion layer can vary as per the kind of material and the conditions, 10 to 1000 micrometer. So, this is extremely good from the properties point of view. It helps to enhance the residual compressive stresses. It also helps to enhance the hardness greater than the substrate. Hardness is greater than of this layer is greater than the substrate. So, thereby it will be improving the abrasive and adhesive wear resistance, and because of the residual compressive stresses, it also increases the tensile strength and the fatigue resistance of the material. So, this is how the different zones are being formed due to the varying concentration of the nitrogen in the surface layers. And if we try to plot the concentration versus the different zones which are formed, so very top surface layers will have the one type of the nitride layer, then there will be another nitride layer in the subsurface zone, and the further subsurface zones there will be a diffusion zone. So, if we plot, this is the compound layer zone and this is the diffusion layer zone. So, here the gamma kind of the nitride is formed, eta kind of, and here thereafter that we will have alpha nitrides, where iron nitrogen will be in diffused state with the iron to form the iron nitride. And if we see the variation in the nitrogen concentration like 10, 8, 6, 4 and 2, then the variation will be like this, is decreasing from 10 to somewhat 8%. This is one zone, corresponding to this area, and then this comes out up to this zone. Then we will have the another zone, and then this zone is a little bit wider, and then we will have third zone. So, this the second zone actually corresponds to this is starts somewhere 5%, and then like this zone. So, here these are the compound layer zones will have the higher nitrogen concentration, which is greater than 4 or 5% of the nitrogen, and below that we will have the low nitrogen content in case of the where nitrogen is in the diffused state in the ferrite. So, this zone corresponds to the very high nitrogen concentration, then the second zone somewhat lower nitrogen concentration, and then further lower nitrogen concentration zone is this alpha, where iron nitride is formed. And the two kinds of the nitrides which are commonly formed, like one is formed in form of the white layer, where very Fe4N kind of the nitride is formed, which is extremely hard and brittle and crack sensitive. This is formed at the surface, and in the diffused zone we may get like 2 to 3 range of the like Fe2 to 3 is the range, and then N. So, this is the iron nitride which is formed in case of the diffused layer zone. Now, if we want to see where, so in this case we have primarily talked about the iron nitride formation, and in iron nitride which is hard and brittle, especially which is formed at the surface. In order to, since in this process we are enhancing the nitrogen concentration at the surface through the enrichment of the nitrogen in the steel component. So, if the steel is like plain carbon steel, where primarily carbon, manganese and silica are present, and sulfur and phosphorus are like impurities. So, balance is the iron. So, iron, because of the higher affinity with the nitrogen, it will be primarily forming the Fe4N or Fe223 nitrogen for property enhancement, but these steels are not that effective for improvement in the hardness and the compressive residual stresses, because iron nitride is not that effective with regard to the property improvement, and there are other nitrides like chromium nitride, aluminum nitride, titanium nitride. These elements form very effective, very hard, very stable nitrides. So, if the steel whose properties are to be modified by the nitriding, if these steels are having some amount of the chromium, aluminum or nitride, then the effectiveness of the process will be much better. So, in that case, if the steel is designed to have the chromium, aluminum, vanadium, titanium, etc., then the formation of their nitrides will be causing the much better improvement in properties. So, we can say there are special category of steels having the aluminum, titanium, chromium, so that they can respond in much better way during the nitriding process. So, with regard to this, if we try to see the effectiveness of the methods, then effectiveness of the methods will be going in like this, wherein if we perform the nitriding for a longer period like 10, 20, 30, 40, 50, 60 like this, it is in hours nitriding time in hours, and the depth which is a realized depth of case hardening realized after nitriding in, of course, micrometer up to if the reference level of the hardness, increase in hardness is 50 HRC. So, the depth up to which 50 HRC hardness is realized through the nitriding process, that depth varies with the nitriding time, but the variation is different for the different steels. Like if we take up the AISI 4340 is one steel which is having chromium as well as controlled content of the carbon. Then if we use, instead of the AISI 4340, if we use AISI 4140 steel, then the depth which will be produced up to the required hardness, that will be much better in case of 4140 as compared to the 4340 steel, and this is attributed to the presence of the different kind of nitride forming elements which are much better as compared to the case of the simple 4340 steel, and maybe for plain carbon steel it will be going like this. So, but for the another steel, there is nitrialloy steel, the rate of increase is much faster. Nitrialloy is still having this, so this will be responding in much faster rate for increase in the hardened depth up to the required hardness during the nitriding. And if we see this depth depth up to which the hardening is being plotted here, it will be like this. So, 100 micrometer, 200, 300, 400 and 500, as compared to the carburizing, which was taken like time of 2 to 4 hours to get the hardness case hardened depth up to like 2000, like 150 to 2000 micrometer. In case of the nitriding, the case hardened depth is like ranging from 100 to 500 micrometer, and while it is taking time, very long time of like 50 to 60 hours. So, although this variation is different for the different category of the steel, but if we compare the two processes directly, then nitriding is slower process. Nitriding is a slower process as compared to that of the carburizing. So, now we will see the conditions under which the nitriding is performed and how it is facilitated. So, as far as the conditions and the reactions which are required to perform for nitriding, say there is an enclosed chamber like this, where the components to be subjected to the nitriding will be placed like this. These are the stacks, and here the components to be processed will be kept, and this entire enclosure is subjected to the high temperature through the external heating. So, this chamber is heated in the range of like say 500 to 590 degrees centigrade, and we know that and then we feed the gas mixture, which primarily consists the ammonia and sometimes the hydrogen mixture. So, these are the gas mixture and the temperature conditions which are used for the nitriding purpose. If we see this temperature range carefully, this is the temperature range below the lower critical temperature in the iron carbon diagram. So, if it is the steel, then the steels when they are heated in the 500 to 590 degrees centigrade, they remain in the ferritic state and no austenitic transformation is observed under these conditions. Primarily, which means carburizing is performed in the austenitic state, while nitriding is performed in the ferritic condition. So, the steel which even during the nitriding will be in the ferritic condition, and the reason for this is that when the nitriding is performed in the ferritic state, the diffusion rate is quite good. So, to exploit this benefit and to avoid the unnecessary high temperature heating, the nitriding is performed in this temperature range of 500 to 590 degrees centigrade. So, we get the much better diffusion rate in the ferritic condition, and when this carbon and when and at this temperature of like 500 to 590 degrees centigrade, when this gas mixture is passed in the chamber, then it will be leading to the certain kind of the reactions like NH3, it will be decomposing into the nitrogen plus hydrogen, and so this is one reaction. So, it will be making the nitrogen available all around the component which is to be processed through the nitriding. Now, this is an example of the gas where gas mixture is fed in the chamber which is heated in this temperature range, so that all the components are processed through the nitriding process. Now, nitriding can be available in 3 different variants, like carburizing we have seen was available in form of like say the pack carburizing or solid carburizing, liquid carburizing, gas carburizing and the vacuum carburizing. Similarly, the nitriding is also used in the form of the 2 variants or 3 variants. One is like salt bath or the liquid nitriding. The second one is the gas nitriding, and third is the plasma nitriding. So, these are the 3 different variants as far as nitriding is concerned, and these 3 variants differ significantly with each other with regard to their process characteristics. So, starting with the liquid nitriding. Liquid nitriding, like we have seen in the case of the liquid carburizing, we use the molten salt bath. So, here also the molten salt bath is used. So, the components will be dipped in the salt bath, and because of this we get the benefit of the rapid heat transfer. So, this shortens the process cycle, short process cycle. So, this process is fast, this is one aspect, and we use the bulk of number of the components can be subjected to the nitriding in one go. So, it is good for the bulk treatment when number of small components needs to be treated, but there are issues like the whatever waste is generated, that will be making the process dirty. Yeah, that is, and it will be making the process dangerous also because of the use of the molten bath, and at the same time this process uses the high initial investment. So, the process the fixed cost is high, initial cost is high, the process is dirty and it is dangerous use of the molten salt bath, but it is quick, the process cycle is quick because of the faster heat transfer, and it can be carried out on the number of components at a time. On the other hand, the gas variant of the nitriding process, the process cycle is medium process cycle, and the cost wise it is reasonable cost, and it consumes and the power consumption is also moderate related with this process. But the negative sides of this process is like the difficult control of this process, gas consumption is high. So, the process control is difficult, gas consumption is high, and it can be applied on the limited components. So, means the applications of this process are very limited. On the other hand, the plasma variant of the process, the plasma process, it is a very effective process, it is very fast and low power or energy consumption, and but the equipment cost is high. So, low energy and the good control over the process, and here the process is fast, low power consumption, but initial high cost of equipment is one aspect. It needs the skilled worker or trained people for performing the plasma nitriding. So, these are the different variants only, but the basic underlying principle of the nitriding process is same what we have talked in detail, that nitrogen content or the surface layers is to be improved, so that we can form the required iron nitride or the nitrides of the other elements for improving the surface properties. Now, I will summarize this presentation. In this presentation, basically I have talked about the underlying principle of the nitriding process and what are the chemical reactions and what are the conditions required for the nitriding process, and there are a few special category of the steels which will perform or which will respond very effectively to the nitriding process for improvement in the surface properties. Thank you for your attention.